So let's begin to look at really some simple data restructuring. Specifically, we will try to analyze charge stability diagrams with some very simple clustering technique. So the clustering technique we are going to consider is the so-called principal component analysis. Imagine that you have some high-dimensional large data sets. So we will have endpoints in k dimensions. I just plotted some dummy points here for you on the two axes. What principal component analysis does, that it defines a p number of vectors, here p equals to 2, the two orange arrows, that best follows the data in a sense of minimal square distance. So basically you are trying to find a direction in which the sort of variation of your data is a minimal. After you found the most prominent direction, you are going to ignore that one and find the second most prominent, and if you wish, third, fourth, fifth most prominent, and so on. These are the so-called principal components, and they help you replot you the data in the directions that are most meaningful in your data set. You are going to have all the math of how this works written down in your reading submodule. When you found these principal components, you can replot your data in the framework where your principal components are the axis. Here on this example blob here, nothing much interesting happened other than everything became a bit more centered. But let's look together if something interesting maybe happens if you try to apply these ideas to your quantum dot charge stability diagrams. So for a charge stability diagrams, we have a lot of measurements and we have them already in 2 dimensions. And then the whole logic will be repeated for these 2-dimensional charge stability images. When you apply this algorithm, what you are going to get is not something super informative, but still something that has some interesting features that are worth looking at. So when you are going to use PCA for your charge stability diagrams, you are going to see something like this. We have these colorful blobs where one color corresponds to one type of dot and the other color the other type. So while these clusters are not super informative in itself, maybe there is some meaning we can actually already decipher even from the simple clustering techniques. So for each charge stability diagram, we give you a red dot or of where it lies in a cluster. So looking at the images below and the red dots, you will quickly realize that if I have a double dot, which is this one and this one, I'm in the purple regime. And if I have a single dot, I am in the blue. But maybe now it also depends on what kind of single dot you have, because it seems that the vertical transitions are sort of in this middle blob that is well separated from everything else, whilst unfortunately the horizontal transitions get sort of meshed up with the double quantum dot. So we didn't get exactly the separation we wanted, but we got some separation. Specifically, the single dots with the vertical transitions, so one of our dots being visible, got separated pretty nicely. When Winnie is walking you through your coding demo, you can think about what it is about how you reorder the data when you do a PCA that this kind of thing happens. And you can also ask yourself, what would you have to do to have the other class more visible? I will leave it at that for now. We will come back to this later on in the lecture. As I said before, the math of this is relatively simple, but it's a lot of algebra. So we wrote it down for you. Go through the analysis of how to do it in the next section, and we will see you on the other side when we move on to the neural networks.